Here's a hologram I made in 1983. It's a 2-inch by 2.5-inch black and white film glass plate that I exposed with laser light, developed, and then spray painted black. Here it is lit up with a cheap LED light. You see three images. The vague one of the woman on the left is a magazine photo. There's a G.I. Joe doll, and then a little antique Cupid doll, and a music box and a circuit board to the right. Here's the same hologram at a drastic sharp angle where you see the profile of the face instead of the full-on. Here it's viewed from another angle, so you don't really see the woman face. The Cupid doll is kind of almost horizontal, and you see the roll of the music box. An angle pointing down so that you can see the face is distorted from the forehead down, and the Cupid doll is almost full face now. My obsession with holography started in 1976. I wanted to send pictures of my newborn son to family in California when I was living in Denmark, and I was always interested in stereo 3D photography. I made a primitive wood flip-flop adapter to a tripod to take two parallel shots for the stereo photos. So from having played around with stereo photography, I was familiar with the word parallax, that you had two parallel images, one that saw the view at the angle from the left eye and one from the right eye, and that would give you the two views that would allow you to see 3D. Well, the Journal of 1976 said that there was something called a hologram that with a single exposure on black and white film could give you full 120-degree moving parallax in both the up and down and the left and right, basically in spherical direction. That amazed me. I could not understand how that could possibly be possible. So shooting a stereo photograph of this tree through the frame, you could get an image of the branches sticking out because you had a left eye view and a right eye view, but only two views, and so things could stick out, but you could never stoop down on the photo, lean the photo to any angle and look up and see the bird. That would be a huge parallax change, or tilt it the other way and see the ball through the frame. And not to mention that you could scan every part of the tree from the top to the trunk to the grass all through one plain image that was taken with a single exposure, not a video or moving images. So holography can best be compared to recording wave patterns in water. It's very different from photography, even though it's done on black and white film. Picture two stones thrown in a pond, and you have the centers up here of the two stones, and in between them you've got the interference pattern where the waves collide and make a pattern. If we put little sticks or markers there where the water waves collided, you end up with a pattern like this. It looks a lot like a lens, and it acts like a lens. When the one side, a single stone, is thrown, the water expands out and actually bends by diffracting off of each one of these little posts if they were stuck in a pond, for example. And the wave reverses. You can see it's not very well drawn here, but we're up at the deadline of submitting this video, so it's bending over, around, reforming from each point, and the wave that's expanding turns into a wave that is contracting. I didn't show it real well here, but if you picture this wave is starting from a center and it's expanding, when it hits that interference pattern, it reverses and it comes in and contracts and splashes up in the center where this one had a stone that would go in. Remember, the two are formed by having the two stones put in and then seeing the pattern of where they were interfering and actually placing physical sticks, say in a imaginary pond, that caused the one wave to bend around and describe the other wave. That's what's happening in holography. Since light waves are so much smaller than our water wave example, we can deal with hundreds of millions or billions of points of light. Now, just look at the difference between having three. Here's the original, what we call the pure light of a reference beam, and that's only one light, and then it's colliding with three different points. That's a real primitive line of, say, three other stones that are thrown. The complex interfering pattern here is no more in that simple lens shape that we saw. Here's a real primitive example of it's more complicated than that, but it would work the same way. When you now threw a single stone, it would bend across here in a way that formed three consecutive splash up points. 1, 2, 3. So throwing the one stone would bend the water waves in a way that they could splash up in three different locations if you had absolutely ideal conditions. That's about as far as you could take water. So here's a primitive drawing of my film plate, the clear glass black and white film seen on the side. Now the light's coming in from a laser, but the laser is spread by a lens so that it no longer becomes just a beam that would go straight through. It's going to bathe everything here because we're putting a lens there. So from the perspective of this side of the film, you're looking down through concentric circles into a point. It's like the single stone. The light's pure coming off the tip of the laser beam, being spread by that. The only reason you're using a laser is to have even waveforms. It has nothing to do with burning, but even waveforms of one color light, one wavelength, make this nice even bathe that is comparable to our single stone thrown in the water. Now we have a primitive object, a G.I. Joe doll, for example, out of plastic or whatever. So the light is going to pass right through this clear film, and when it hits each area of this object, it's going to bounce back. I'm not going to be able to draw it, but just multiple wavelengths coming off, like the three we saw before, but there's going to be millions of points. Each point of the glistening plastic is going to come back with overlapping wave patterns that are going to intersect at the film with the one even pattern. So we could compare this to the single stone thrown in a pond, and instead of our three stones in the other example, we'd compare this to throwing a handful of sand. It's just way more of a pattern than I can draw, coming complex back from each point, but they intersect here at the film. And that's key, and that's why black and white film at that resolution is accurate enough to record that extremely complicated pattern, that when the object is taken away and the film is developed, a single light again will reproduce the entire wave set from all angles with that full parallax. It sounds hard to believe, but it works. And it works both ways. If you were crazy enough to position the finished hologram back in exactly the same position from the object and lit the object up with the same lighting, then all the light from here would recombine through that grading pattern that was recorded as black and white lines microscopically a 5,000th of a millimeter on black and white film of extreme high resolution. All those overlapping wave patterns would then reunite and make one big bright spot that had been the laser point at the beginning of the cone. So it's a true matrix that works in both directions. You can see at the top of the screen here the YouTube video that I did. It's too slow, my internet connection now, to get it to roll. It might move a few seconds here. Maybe I can move it with the hand. You can just kind of, but you could go to that site up here and see the whole moving video, so you get an idea how that actually is, moving in. I showed a lot of still shots, but anyway. I must admit I bit off a little more than I could chew on this video, trying to explain everything at the same time and right up against the deadline for Khan Academy. So anyway, Trying to sign off at 5:42 Hawaii time, which is going to be very close to midnight if they're going on Eastern time, so hopefully I'll get this submitted in time.